All right, so here's our asteroid. And first question is about escape speed. And so just conceptually, so you understand what escape speed is. If you throw something up in the air, I have this pen here, I could throw it up in the air. Uh, and if I did that, once I let go of it, gravity slows it down. It slows it down, slows it down, slows it down, slows it down, hits a velocity of zero, and then it speeds it up, speeds it up, speeds it up. But the point is that as something moves away from a planet, the planet's gravity slows it down and it makes it go slower and slower and slower and slower. And then eventually it stops and brings it back. So, speed is the speed you have to give something so that as gravity inevitably slows it down and makes it go slower and slower and slower and slower and slower, by the time it finally gets to a velocity of zero, it is so far away from the planet that the planet cannot bring it back again. And theoretically, that has to be a distance of infinity away. Because even if you're just a little bit closer than infinity, there is going to be a little bit of gravitational force. And that force is, if your velocity is zero, just a little bit before infinity, you're going to have a little bit of gravitational force acting on you, and it's going to bring you back again. So you have to get to a distance of infinity at the moment that the velocity is equal to zero, so that at that point you're so far away that gravity can't speed you back up again. So the way that we solve that, this is a tricky problem because as you move away from the planet, certainly the acceleration due to gravity of the planet changes. And oftentimes when you have a changing, well, certainly when you have a changing acceleration, you can't use motion equations. So oftentimes your backup is the law of conservation of energy, or UCWC, and that's exactly what we're going to use here. So we're going to do U at A plus K at A plus W and C equals U at B plus K at B. So A is going to be the surface of the planet, and B is going to be at infinity. Um, a reminder that when you're calculating gravitational potential energy on a planetary scale, we use the equation negative GMM over R. We don't use the equation mgy because little g changes. As you go further and further away from that planet, little g changes. So we have to use this equation right here. Now, they did not give us the mass of this asteroid. However, they did give us that little g equals 3 meters per second squared. So maybe our first step is to use that information to figure out the mass of the asteroid. Now, little g fits into our equation for weight, Fg equals mg. We don't have enough information to solve just that. This m refers to a mass that would be on the surface of the planet. That's not the mass of the planet. We also have an equation Fg equals gmm over r squared. Now they both equal the same Fg, so they equal each other. So mg equals gmm over r squared. The little m, that's the thing that's on the surface of the planet, cancels out. And now we'll be able to figure out the mass of the planet. So they're telling us that g equals 3. Capital G, 6.67 times 10 to the negative 11. That's true everywhere in the universe. M is our unknown. The radius of the planet is 500 kilometers. We need to do that in meters, so we have to multiply by 1,000, and we square it on the bottom of that equation. So let's see what my calculator gives me for the mass of this asteroid. So I'm going to take 3, I'm going to take 500,000, I'm going to square that 500,000, multiply by 3. I'm going to divide by 6.67 times 10 to the negative 11, and I'm going to get a very large number. The mass is 1.12 times 10 to the 22nd kilograms. However, the Earth's mass is times 10 to the 24th kilograms, so this is 1/100th the mass of the Earth, approximately. So that seems like a realistic answer. Okay, now I can get to UCWC. All right, at A, we have negative G. M is the mass of the planet. M is the mass of the thing that we're trying to throw off the planet. R, I'm going to use capital R to represent the actual radius of the planet itself. That's at point A. Also, we need to give it some speed. We need to give it escape speed there, 1/2 mv squared. Again, little m is the object that we're throwing off the planet. There is no WNC. Non-conservative forces are forces that don't just switch energy between kinetic and potential. The only force that's acting on this is gravity, and gravity does switch energy between kinetic and potential. So gravity is a conservative force, so that part is 0. On the other side of the equation, The potential energy at B, that's at infinity. Well, let me put it into the equation, but hopefully you realize that's going to be 0. When you divide by infinity, you get 0. And also we said that's the spot where we want, finally, the velocity to be equal to be 0. So actually the entire right-hand side of the equation is 0. That's okay, we had a negative sign here. By the way, our little m cancels out, and we can solve for v, and v is equal to the square root of 2gm over r. So let's put in those numbers to get that answer. G is 6.67 times 10 to the negative 11. The mass of the planet we discovered is 1.12 times 10 to the 22nd, and then r is 500,000. And let's see what we get there. So 6.67 times 10 to the negative 11 times 2 times 1.12 times 10 to the 22nd divided by 500,000. And I got to take the square root at the end. And my answer is 1,728.6 meters per second. That's far less than the Earth's escape speed. I don't remember exactly what it is, but that's going to be a realistic answer. You know, I just want to point something out real quick. Maybe a quicker way that we could have solved this. You know what? I changed my mind on that. Ignore that. This was good enough. So let's go on to part B. Part B says, how far from the Earth's surface will a particle go if it leaves the asteroid surface with a radial speed of 1,000 meters per second? Okay, so same basic picture here, but now this object that's at the surface of the planet has a radial speed, which means it's parallel to the radius of 1,000 meters per second. And the question is, how far out is it going to go? So notice that this is significantly less than the escape speed, so it's not going to go to infinity. But it's going to be the same method to solve the problem. U at A plus K at A plus WNC equals U at B plus K at B. So once again, at A, we have negative G, the mass of the planet, the mass of the object divided by the radius of the planet, plus 1/2 the mass of the object, 1,000, that's how fast it's going there, squared. And then over here, we have negative GMM. Little r is the variable that we're trying to solve for. How far away from the center of the planet does it go? And at the furthest point, it's going to have a velocity and therefore a kinetic energy of 0. So m cancels out. And let's see here. Let's put some numbers into this. Negative 6.67 times 10 to the negative 11 for G. What was the mass that we found? Oh, 1.12 times 10 to the 22. 1.12 times 10 to the 22. The radius is 500,000 plus 1/2 times 1,000 squared equals negative 6.67 times 10 to the negative 11 times 1.12 times 10 to the 22nd and divided by r. So this is going to be a little bit of fun here on my calculator. Hopefully I can do this without making a mistake. 6.67 times 10 to the negative 11, 1.12 times 10 to the 22nd, multiplying those together, dividing by 500,000. That one's actually negative. And then 1,000 squared divided by 2, add to that previous one, okay. And then I actually need to switch things over here. So I'm going to inverse, I think I'm almost there, 6.67 times 10 to the negative 11 times 1.12 times 10 to the 22nd. And that's negative, and multiplied by that previous answer. And the answer that I'm getting, that I certainly hope is correct, is, let's see, 751,488.8. So that's 751,488.8 meters away. That's how far that thing is going to go from the surface of the planet. There's a part C here, and the question is, with what speed will an object hit the asteroid if it's dropped from 1,000 kilometers above the surface? Ooh, you know what? I just noticed in part B, the actual question was how far above the surface of the planet. They get tricky like this sometimes. So the question is not how far from the center of the planet. And when you use this equation right here, this r is always the distance from the center of the planet. It's the distance between the centers of the two objects. So this would be the distance between the center of this object and the center of the planet. But they specifically said how far above the surface. Sometimes we call that the altitude. So I need to subtract. I'm going to subtract from this the radius of the planet, which is, as I recall, 500,000. So my actual answer to the question that they asked would be 251,488.8. That's how far above the surface of the planet it will go. Good thing I checked that. All right, last question. It's actually an asteroid, isn't it? I was calling it a planet. Anyway, this object, they say, is 1,000 kilometers above the surface. Again, not from center to center, but above the surface. And if it's let go from rest, how fast will it be going when it strikes the surface? It's another upward problem. Let's call this A. Let's call this B. So the potential at A would be negative G M M over, and now this distance is 1,000 kilometers. So I have to multiply that by 1,000. That actually makes it 1,000,000 meters plus 500,000, which is the radius of the planet. Because again, in this equation, the r in the bottom of the fraction of this equation is the distance between the centers of the two objects. So I needed to add that. Okay, and so that's at point A. It does start from rest, so it has a velocity of 0. There are no non-conservative forces. Now, how about when it hits the planet? Well, when it hits the planet, we're going to have negative GMM over 500,000 and plus 1/2 mv squared. And that's the v that we're trying to find. So once again, it doesn't matter what the mass of the object is. Plus, it looks as though I can subtract this over to the other side and factor out a GM. That'll make things a little bit easier on my calculator. So I'm going to have GM and 1 over 500,000 minus 1 over 1,500,000. And that's equal to 1/2 v squared. Again, I'm hoping I did the algebra right there. Let's give it a try. 6.67 times 10 to the negative 11 times the mass of the planet, which was 1.22 times 10 to the 22. And then I have 500,000, inverse of that, and 1,500,000, inverse of that. Oops, that's the negative of that, but I needed to do that anyway. Inverse of that. Add those two together, multiply by that, multiply by 2, take the square root, and I have an answer of 1,473 meters per second. And again, that is less than the escape speed, which is how fast it would be going if it had been dropped from just inside infinity. So I feel like I'm feeling pretty good about that answer too.